Hi there, and welcome to today's class. For today's class, we're looking at the concept of resonance frequency. Now, resonance frequency is a phenomenon that occurs in an RLC circuit. That means a circuit that contains resistors, inductors, and capacitor. Now, before then, what is resonance frequency? By definition, resonance frequency is the frequency at which the amplitude of the current is maximum and the circuit would oscillate if not driven by a voltage source. All right, so that's the definition of resonance frequency. Also, we can say resonance is said to occur in an in an AC series circuit when the maximum current is obtained from such a circuit. All right, so for this concept, let's call resonance frequency F naught. So we'll be using F naught to represent resonance frequency. All right, so here's something to note. At resonance frequency, the reactance of the inductor is equal to the reactance of the capacitor. I think that's a condition to note when it comes to solving problems on resonance frequency. So I'm saying at resonance frequency, so at F naught, the reactance of the inductor, that's XL, is equal to the reactance of the capacitor. Of course, we've discussed all of this in our previous classes. If you missed the class on AC and AC circuit, I'll leave a link to those classes in the description of this video. All right, so you can check out the videos later. Now, for this one here, let's proceed. We said this is called the reactance of the inductor, and we said the formula for reactance of inductor is 2 pi FL. Also, this one here, XC, is called the reactance of the capacitor. The formula for this is 1 all over 2 pi FC. All right. All of this has already been discussed in our previous class. All right. So make sure you check this up if you missed the class. All right. So let's get this condition here. So if this is true, and we are saying that at resonance frequency, this is equal to this, that means this value here becomes 2 pi FL is equal to this one here, which is 1 all over 2 pi FC. Now, since this condition here, which is XL being equal to XC, occurs at resonance frequency, we'll change the F from ordinary F to F naught, indicating resonance frequency. Also here, this becomes F naught. So please understand why I'm changing this from the normal F to F naught. I'm changing to F naught because for this condition, the frequency becomes the resonance frequency. So I'm having F naught. Our task here would be to make F naught to be subject of the formula, which in this case, I would have to simply cross multiply. So this multiplies this. I'm having 2 pi F naught L multiplies this here, which is 2 pi F naught C is equal to, I'm having 1 times 1, which is 1. So I have this. If I expand this bracket here, I'm having 2 times 2, that gives me 4. Pi times pi, that gives me pi squared. F naught times F naught, that gives you F naught squared. L times C is LC. I have this. Okay, so this is equal to 1. All right, now we're trying to get the value of F naught. So I'll try to make F naught to be subject to the formula here, in which in this case, that would mean dividing here by everything attached to F naught, which is 4 pi squared LC, divide here by 4 pi squared LC, divide here 2 by 4 pi squared LC. All right, so what do you get? From here, you can see that this would cancel this two. L cancels L, C cancels L. C cancels C. So I'm left with F naught squared. So it means that F naught squared is equal to what I have here, 1 all over 4 pi squared LC. Obviously, to get f naught, I'd have to take the square root of both sides. Take square root of this becomes the square root of f naught, excuse me, small f naught squared is equal to, of course, capital F there means force. For frequency, we use small letter f. So square root of this one here, 1 all over 4 pi squared LC. I have this. In this case here, square cancels square root. You have that the resonance frequency F naught is equal to. Now, when we have a case like this, using the concept of indices, it is correct if you take square root of numerator, which is square root of 1 all over square root of denominator, which is square root of denominator is 4 pi squared LC. So I have this. This is mathematically correct, okay? Square root of numerator all over square root of denominator. I have this. All right, so from this, what's the next thing here? I will have that f naught is equal to square root of 1 is 1 all over. For this case, the square root I can take the square root of each of the terms here. But what I'll do is this. If I look at this very well, you can see that 4 has a square root, which is 2. Pi squared has a square root, which is pi. Why these two are not perfect squares? So what I'll do is very simple. I'll take the square root of the terms that are perfect squares, which include 4 and pi squared. So this of 4 and pi squared will now multiply the square root of the terms that are not perfect square, which are L and C. That's LC. This is mathematically correct. So from here to, if I proceed with my solving, I'll have that resonance frequency F naught is equal to, I have 1 all over root 4 is 2 root pi squared, because the square root will cancel the square. I'll be left with pi, then left with square root of L times C is LC. So this now becomes the formula for calculating resonance frequency. 1 all over 2 pi root LC. All right, so let's see how we can apply this concept in solving problems. Okay, before we solve some problems, let's recall something. Recall that there's something called angular frequency. And we know that angular frequency, omega, is equal to 2 pi f. All right, so if this is true now, if I have here as resonance frequency, that's f naught, I can also have here as resonance angular frequency. So in other words, we can say that resonance angular frequency is equal to 2 pi resonance frequency. And if this is true, I can work on this from here. I can simply bring 2 pi up here. It's mathematically correct. This 2 comes up here. You can use it. It's called cross multiplication. So it's possible that these 2 come up here. So you now have something that looks like, if this 2 comes here, I'm having 2 pi, then this f naught is equal to this here, 1 all over root LC. So this is correct. But we know that 2 pi f naught is equal to angular resonance frequency, right? So it means that in this case here, this man, angular resonance frequency is equal to 1 all over root LC. So please note these two formulas. Note that resonance frequency is equal to 1 over 2 pi root LC, and angular resonance frequency omega naught is equal to 1 all over root LC. All right, so with these two concepts noted, let's see how we can solve problems on this. All right, before we solve some questions, let's look at a concept that I think is very important when it comes to the concept of resonance frequency. Now, from our previous class, which I said I will leave a link in the description of this video, we said the voltage supply across an RLC circuit, series circuit, okay? So we said the voltage supply across an RLC series circuit is given by V is equal to I for an RLC for an RLC series circuit, it becomes ZRLC. What we said, ZRLC is called the impedance of the circuit. Now, if this is true, also recall that in our previous class, we got the formula for ZRLC as equal to the square root of R squared plus XL minus XC all squared. Excuse me more. Cut, please, cut, please. All right. Um, R squared. All right. Right. Here. All right. So we got this. For this case here, now recall that at the resonance frequency, we said that XL is equal to XC. If I impute this condition into this, you have that ZRLC, which is the impedance of the RLC series circuit, is equal to, you have square root of R squared plus, now since these two terms are the same thing, if they're of the same value, if you have two terms of the same value subtracting, it gives you 0, right? Example, 3 minus 3, 5 minus 5, and etc. So since they have the same value, if they subtract, it should give you 0. So plus 0 squared. So I have this. So work on this. It means that ZRLC is equal to the square root of, I'm having R squared plus 0 squared is 0. Work on this, you have that ZRLC is equal to the square root of R squared plus 0. Anything plus 0 is that thing, so R squared. So in this case here, obviously you have that ZRLC is equal to square cancel square root. You have R. So I have this. Now the R, so I have R here as this. So it means that in this case, so it means that therefore, if you have V is equal to I ZRLC, it means that the impedance of an RLC circuit at resonance is R, right? It's R. So that means that for here, now recall that we said resonance occurs at the maximum current. So it means that V will no longer be V, but V naught is equal to I. Since it's at resonance frequency, we said maximum current. It occurs at the point where maximum current is reached. So it becomes I naught, and then ZRLC becomes R. So I have this. So note that at resonance frequency, you have that V naught is equal to I naught R. Okay? The reason why we change this V and I to V naught and I naught is that the resonance frequency occurs at what there? The maximum current, as we said earlier. All right. So if I have maximum current, obviously I also have maximum voltage. Right. So this I naught means maximum current, maximum voltage. Also at resonance frequency, ZRLC, which is called the impedance of the RLC series circuit, is equal to R as derived. So you have this equation. All right. So with this now, let's now do the past. So with this now, let's try some questions. All right. So let's look at this question here. This question here says, an AC voltage of amplitude 2.0 volts is connected in an RLC series circuit if the resistance in the circuit is 5 ohms and the inductance and capacitance are 3 millihenry and 0.05 microfarad respectively. calculate I, the resonance frequency F naught, II, the maximum AC current at resonance. All right. So in this case here, solution, let's try to, as usual, list out my given parameters. So what are you given here? So what are we given here? Given number one, they said an AC voltage of amplitude 2.0 volts. So it means the peak voltage, right, is 2.0 volts. Because they said this is the word amplitude, and amplitude is like the highest value. That becomes the peak or the maximum voltage. That's it. It's connected to an RLC series circuit. They said if the resistance in the circuit is 5 ohms, so our resistance is equal to 5 ohms, okay? And the inductance and capacitance, number 3, inductance is L. The value is about 3 millihenry. And, okay, so let me do a conversion for this very fast. This will be equal to 3 times 10 to the power minus 3 Henry. So milli is 10 to the power minus 3. That's milli of milli. Number 4, you're also given the capacitance. Capacitance is C. The value here is 0.05. So I have 0.05 microfarad. Putting values becomes 0.05. Micro is 10 to the power minus 6. So 10 to the power minus 6 farad. So I have this. All right. So you have to find what? Calculate the resonance frequency. Solution. Okay, which is solution? Okay. Number one, you have to find resonance frequency. Resonance frequency, which is F naught. We said F naught is equal to 1 all over 2 pi square root of LC or L times C. All right, input values, that's equal to 1 all over 2 pi into the square root of L. The value of L is this, 3 times 10 to the power minus 3 into C. The value of C is this, 0.05 times 10 to the power minus 6. All right, so I have this. So if I punch this, this is equal to, I can punch this a whole, right? Okay, let's let me get my calculator. Okay, so I have this as 1 all over 2 pi, then square root of 3 times 10 to the power minus 3 multiplied by 0.05 times 10 to the power minus 6. So on punching this, I have my answer here, F naught, as being equal to 12994.95 hertz. So its frequency, it should be in hertz. So I have this as my resonance frequency. So that's the value here. Just in case you're asked to convert to kilo, kilo is 10 to the power 3. So just move 3 times here. 1, 2, 3. You have this. And that will be equal to 12.99 kilohertz. Or you can say approximately 13 kilohertz if you want to. Or you can just simply leave it at this point here. It's still correct. Right, the next part of this question, the B part. B part said, you find the maximum AC current at resonance. If you look for maximum current, maximum current is I naught. B, you have to find max current. Max current, we said it's I naught. And from what we had before, we derived something here. We said for resonance, recall that V naught is equal to I naught times R. So if I'm asked to find I naught, I'll have to divide this by R, such that this cancels this. So I have that I naught is equal to V naught. For V naught, right, so we have V naught here as 2.0 volts, which is 2 all over. We have the resistance as 5, which is 5. From here, if you punch this, would have that I naught, the maximum current, is equal to 2 over 5. That should give you about 0.4. Current is in amperes. The value becomes 0.4 amperes. So this is how to solve this question. All right, so let's look at this question here. This question says, if the resonance frequency is 15.0 millihertz, find the angular resonance frequency. All right, so solution here. So in this case here, we're given number one, the resonance frequency, that's F naught. We're given the value as 15 millihertz. And you're asked to find the angular resonance frequency. That's omega naught equal to unknown. Now recall that we said omega naught angular resonance frequency is equal to 2 pi resonance frequency. So from here, we'll have that value is equal to 2 pi, the value of F naught. This case here is given in milli, so I'd have to convert it to hertz. Of course, it becomes 15 times milli is 10 to the power minus 3 hertz. So I have this, all right? So I have 2 pi, then resonance frequency as this. If I multiply this, you have that the angular resonance frequency is equal to, so if I punch this, I have 2 pi, then I have this. All right, so if I punch this, this gives me about 0.094. All right, so I have about 0.094. My unit here is in radian per second. So please note that the SI unit for this is radian per second. So the SI unit for angular resonance frequency is rad per second. So the answer is simply 0.094 radians per second. Let's take one final question on resonance frequency. All right, so let's try this final question. This question says, what will be the inductance of a circuit having a capacitance of 0.25 kilofarad if the resonance frequency produced is 115 hertz? All right, so let's get this done. Solution. As always, our first task would be to list out given parameters. What's the first thing I'm given there? The first thing I'm given there, we are asked to find the inductance for which a circuit having a capacitance C is equal to 0.25 kilofarad, okay, has a resonance frequency F naught as equal to 115 hertz. So 115 hertz. You have to find 3, the value of the inductance. The inductance is unknown. Let's get this done. So how do we solve this? So for this case here, my first task would be to recall the formula for resonance frequency. So recall that for resonance frequency, your formula is 1 all over 2 pi root LC. So I have this. All right, so with this being the case, what's next here? Let's substitute value. This value here, by the way, so let's convert C. C is about 0.25 kilofarad, and that's equal to 0.25 kilo is 10 to the power 3 farad. The capacitance is equal to, if I multiply this, I'll have 250 as my answer. So 250 farad as your value. All right, so with this taking, we'll have that F naught is 115 is equal to 1 all over 2 pi. So 2 pi into the square root of L times C. The value of C is 250. So I have 250. So you have this one here. It all depends on how well you know how to solve your fractions, or how well you can go through mathematical concepts. You could as well choose to make L to be subject to the formula first before solving this. But for this, we'll do a bit of mathematical manipulation here. And this would now be 115 is equal to 1 all over. This gives me 2 pi. So I'm having 2 pi into, now to solve this one here, it's perfectly okay to take the terms in this square root individually. That means I'm saying root L multiplied by root 250. This is perfectly correct. So this is still okay. All right, so you can separate them and solve like this. All right, so if this is true, I'll have my work here as 115 being equal to, I have 1 all over. If I multiply 2 times pi times root 250, so I'm punching 2 times pi times root 250. Punch that, I have 99.35 approximately, then root L. So I have that. So 2 times pi times root 250 gives you 99.35. Then you now have your root L. From here, my next task would be to cross multiply this times this. So 115 times 99.35 root L is equal to 1 times 1 is 1. All right, to get L, first of all, divide here by 115 times 99.35, or you could still choose to go ahead to multiply these two first, get your value before dividing. You have the same answer. So divided by 115 times 99.35. You have this. All right. So from here, this cancels this cancels this. So you now have that root L is equal to, so I'm having 1 all over 115 times 115 times 99.35. So this gives me about 1 all over. Okay, I think everything here. So if I punch all of this, okay, so everything here gives me about 8.75 8.75 times 10 to the power. From here, if I count this, I'm having 1, 2, 3, 4, 5 minus 5. Okay, I have this. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay, so I have this. From here, it means that L is equal to, of course, I'll have to square both sides. Yeah. Okay. So this is this one here. So square both sides, it becomes root L. I will square this is equal to, also square this, 8.75 times 10 to the power minus 2 minus 5 all square. So from here, square cancels square root. I'll have that L is equal to, so if I square this, I'm having 8.75 times 10 to the power minus 5 all square. Right, all square. And that will give about 7.66 times 10 to the power. Let's say this gives you 1, 2, 3, 4, 5, 6, 7, 8, 9. So 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. So 10 to the power minus 9. This is inductance. Inductance is measured in Henry. But again, we know that 10 to the power minus 9 is a prefix in physics known as nano. And nano is a small n. So it means that L, the inductance, will be equal to 7.66 into times. This one becomes nano Henry, right? So Henry is the SI unit for inductance. So hence L is now equal to, multiply this, I have 7.66 nano Henry. So this would be the value of the inductance. So this is how we solve this question. Right, so if you enjoyed the class, simply like this video and leave a comment. Also, subscribe to this channel if you've not yet subscribed. Of course, too, you can also check out my other classes. I have over 100 plus classes on mathematics, physics, and chemistry. So you can check it up on my website. Simply visit www.jonahimmanuel.com/courses and you see the JAMB/WAEC classes. See you in the next class.